Hi, this is my video number 2. In this video, I'll give one more example on the eigenvalue problem. Yeah, just a continuation from the last video. So in this example, we consider the problem y double prime plus lambda y equal to 0 with boundary condition y prime 0 is 0 and y prime c is 0. So if you compare this with the previous example, the problem is the same except that the boundary condition is different. Yeah. So in this case, we consider various lambda. Yeah. First, we consider for lambda positive. In the previous case, you can also consider lambda positive and negative as negative positive. Positive 0 and negative as well. Yeah. And we know that the general solution, is given as y c1 cos sub lambda x plus c2 sine sub lambda x. Yeah. So now, in order to use the boundary condition here, so the initial condition here, so you can differentiate this. That give you y prime is negative lambda c1 sine x sine sub lambda x plus that one is lambda c2 cos lambda x. Yeah. And then we use the boundary condition, the initial condition. So we have y prime 0. Yeah, y prime 0. That will give you that one is 0. So that gives you c2 is 0. Right, that gives you c2 0. So therefore our solution is y is c1 cos lambda x. Okay. And then for the second boundary condition, we differentiate this. We have negative lambda c1 sine lambda x, and then we use the boundary condition, the initial condition. C is that lambda c1 sine lambda x, so lambda c, right, that equal to 0. Okay, so c1 cannot be 0 because if c2 is already 0. If c1 is 0, then we have a trivial solution. We don't want trivial solution, so therefore c1 cannot be 0. So therefore we have sine lambda c that must equal to 0. Okay, so then we have lambda c, so lambda c, this is n pi, for n equal to 1, 2, 3 and so on. Because when n equal to 0, we have shown in the previous example that it will give a trivial solution. So we remove n equal to 0. Now then we have lambda squared, lambda this n squared pi squared over c squared. So now having this, the corresponding eigenfunction, so we can write the eigenvalue now. The eigenvalues is lambda n is equal to n squared pi squared over c squared. So the corresponding eigenvalue, so therefore eigenfunction the corresponding eigenfunction, we have yn is equal to cn cos. We have set n that give you n pi over c x for n 1, 2, and so on. Okay, so now if we consider that one for the first case, lambda positive. Now if we consider lambda 0, so what we have, our equation becomes y double prime is 0. So that gives a solution, the general solution as y equal to let's say a naught plus b a1x. Okay, that's the general solution. Then we use the given initial condition that y prime 0, that we have a1 that equal to 0. So therefore our solution is y equal to a naught. And the second boundary condition, we have y prime c, which is 0. Okay, b prime c, that's 0. So therefore it satisfies those this y satisfy the condition, the equation given. So therefore those are the solution. So y equal to a naught is also the solution to that system. So therefore the lambda, so therefore lambda equal to 0 is the eigenvalue, and the corresponding eigenfunction, and the corresponding eigenfunction, we have yn is equal to cn which one, cn cos n pi over c x for n equal to 0, 1, 2, and so on. Yeah, we can consider n equal to 0 because we have shown here when lambda is 0, so we have everything 0 there. Okay, that part is 0. So it also gives us the non-trivial solution, so which means this lambda equal to 0 is also the eigenvalue. So therefore the eigenfunction can be written as that. Now if you consider for lambda negative, okay, so if you consider lambda negative, and we may let lambda equal to negative k squared, because this is to make our written much easier where k positive. So you can see here when k is positive squared and we have negative, so lambda is always negative now. So the general solution here, we have the general solution, we have y equal to c1 cos kx plus c2 sin kx. All right, and then we use the given initial condition, we differentiate this one y prime, that we have k c1 sin kx plus k c2 cos k kx. Now then apply the boundary condition. We have y prime, the initial condition y prime is 0, so we have y prime 0, that will give you 0, so therefore that one not 0, so c2 is 0, so we have c2 equal to 0. Okay, so therefore our solution is, since c2 is 0, our solution y is given as c1 cos kx. Now we use the second initial condition. We have y prime, this is k c1 cos k, this is I think c, so that kc that equal to 0. So from there we have our c1 is equal to 0. So therefore in this case we have a trivial solution. Okay, so in this case we have I can say this for lambda less than 0 we give a trivial solution. So therefore lambda negative is not the eigenvalue. So put them together. So we have put them together. So we have the eigenvalue. So therefore the eigenvalue for the problem, for the given problem, is lambda n is n squared pi squared over c squared for n equal to 0, 1, 2, 3 and so on. Alright, and the corresponding eigenfunction yn is cn cos n pi over c x for n equal to 0, 1, 2 and so on. Okay, so this is the solution for the second example. Alright, now I want to give you one more example, but before that let me define the orthogonal with respect to the wave function and as well as the orthonormal. So what is the definition? So definition for the orthogonal, so with two functions, we say y1, y2 are orthogonal with respect to wave function R on interval a b if it satisfies that condition. Integrate ab a y I y j dx that equal to 0 if I different than j and equal to different than 0 if I equal to j. Okay, so this is the definition for orthogonal, and definition for orthonormal, we have y is orthonormal if you integrate from a to b yn squared x rn x dx that equal to 0. That equal to 1. This we call it as a orthonormal. So in this case, this is also respect to x. That x. This is also respect to x. This is also function of x. Now, I want to give the example on orthonormal system. Example. Let's say we have that problem, y prime plus lambda y equal to 0, subject to the initial condition y0 is 0 and y prime pi is 0. Again, we just changed the initial condition. Okay, so from this, I think you can do the rest of it. Just the same process. You can find the eigenvalue is given as negative 2n minus 1 squared over 4. Okay, so therefore our eigenfunction yn is given as, we have cn sine 2n minus 1 over 2 x. Okay, how to find this? I leave it as an exercise to you. Okay, now if we apply the orthonormal formula to find the orthonormal system, all right, so we have the orthonormal, what we have integrate from a to b y squared x rx dx that equal to 1. All right, so we apply to this function. So we have integrate, so we integrate from a to b. Our ab is from 0 to pi. This is the initial condition, 0 to pi. All right, so this is the initial condition from 0 to pi. So we integrate from 0 to pi, and our eigenvalue, our eigenfunction, we have c n squared sine squared 2n minus 1 over 2 x dx. So in this case, we take r equal to 1. All right, and then you can evaluate this. This is equal to 1 because we need equal to 1. Then you can rewrite this as a cn squared, integrate from 0 to pi. You can use the appropriate identity for that. That gives you half minus half cos 2n minus 1 x dx, that's equal to 1. Solve that. Okay, you solve that, you will have cn squared pi over 2 that equal to 1. So therefore we have cn is equal to square root 2 over pi. Okay, so therefore the autonomous system of the eigenfunction is given as we have 2 over pi sine 2n minus 1 over 2 x n from 1 to infinity. Yeah. Okay, so this is the example of I put an extra example for the how to find the eigenvalue and eigenfunction, and as well as in the second example here, in this case I gave you the example of how to find the autonomous system of the eigenfunction, where the eigenfunction we obtain from the given problem. Okay, so what I have done in these two videos, in the first videos I've discussed on what is the eigenvalue and eigenfunction. Then I give you the example, and as well as in the second video I just focus on giving you an example, another example on the eigenvalue problem, and then another example on the autonomous system of the eigenvalue from the given problem. All right, so with that I thank you. We continue in the next video.